Did you know that the United States relies heavily on imports for rare earth elements? In fact, the US is about 90% import reliant on rare earth elements. Because of this dependence, these elements are officially classified as critical minerals by the US government. This heavy reliance on imports creates significant supply risks as the demand continues to increase. So the question is, how can we secure a reliable supply of rare earth elements in the United States? What are these elements? Rare earth elements include all the lanthanides plus scandium and yttrium, and they are usually categorized into two groups, light and heavy rare earth elements. These elements are important for clean energy technologies such as windmills and electric vehicles. A large amount of these elements are also used in defense as well. As the world transitions towards cleaner energy systems, the demand for rare earth elements is growing rapidly. Because of this rising demand, it is important to explore all the viable secondary sources of these elements. One such promising source is acid mine drainage, or AMD for short. AMD is an acidic water stream that is generated due to mining activity, and it has rendered more than 5,500 miles of streams biologically dead in Pennsylvania alone. However, AMD also contains valuable critical minerals, including rare earth elements. At Penn State Center for Critical Minerals, we already have a process developed to treat acid mine drainage while recovering these critical elements using a three-stage precipitation process as shown here. This process also produces a mixed rare earth concentrate with over 95% purity. However, separating this mixed rare earth concentrate into individual elements or groups is a major challenge, as these elements behave very similarly in water. One way to measure the separation difficulty is through something called a separation factor. For example, metals like cobalt and nickel have a separation factor of about 4, meaning they can be separated relatively easily. But for adjacent rare earth elements such as europium and gadolinium, the separation factor is only about 1.1. Any value below 1.5 is considered very difficult to separate. Because of this, the traditional solvent extraction processes require 40 to 50 repetitive stages and can generate large amounts of chemical waste. So the key challenge is, how can we separate rare earth elements efficiently and sustainably? This is where my research comes in. My name is Triveni Gangadhari and I am a PhD student at Penn State. Instead of using traditional solvent-based methods, I am developing a greener technique using ion exchange resins and a complexing agent called ethylene diamine tetraacetic acid, shortly EDTA. Ion exchange resins are small polymer beads with functional groups that can capture rare earths from solution. These resins can be used multiple times and do not generate any hazardous waste. Importantly, EDTA as a complexing agent binds more strongly to heavy rare earth elements than to light rare earth elements, and we are using this difference to perform the separation. Let's look at the process now. The separation process occurs in 2 steps. In step 1, the mixed rare earth element solution is passed through a column packed with ion exchange resins, where these resins capture both light and heavy rare earth elements through this functional group. In step 2, we pass EDTA solution to selectively recover heavy rare earths while keeping most of the light rare earths on the resin. And using this method, within 2 cycles, we successfully separated heavy rare earth elements from light rare earth elements with a purity of about 97%. This demonstrates that sustainable rare earth element separation is possible. Moreover, environmental challenges like AMD can be turned into opportunities for sustainable critical mineral recovery right here in the United States to avoid any supply chain risks. Innovative separation technologies like these can protect both the planet and national mineral interests. This project was made possible by a generous grant from Department of Energy. This work wouldn't be possible without the productive collaboration within the Center for Critical Minerals. We also have the amazing support from our supervisors, Dr. Sharma Pisupati and Dr. Mohammad Razai at Penn State. Finally, thank you for your time and interest in our research.